Well, we're getting near the end of the oil testing. So, first off, I wanted to thank everybody that has sent me samples of oil to test, and also provided donations to help cover what this cost. So I kind of thought I'd go over what I'm doing again here. So basically, it's no secret that the oils that are being supplied today are mostly made for newer engines. Newer engines meaning they're water cooled and overhead cam, usually multi-valve, so the spring pressures are very light, and therefore the oils don't need to have the ability to handle a high load. So I had an earlier SCAR tester years ago that I experimented with a bit and never really found it to give me any real valuable information. So this here should be called the no SCAR tester, because what I'm looking for is the ability of the oil to support the follower without contact and without a scar. Because as soon as there's a scar, then the camshaft and lifter are gone. They're failed. So, got a 1-horse motor here. It's 3,450 RPM. There's a bearing race on the arbor. This is a cooling motor. It supplies a heavy blast of air, and the cup has cooling fins on it that allows that air to go under it. Here is the heating element. The heating element is controlled by this unit here. It's a temperature controller, and it has a thermocouple that fits in the little hole in the bottom of the bowl. Also in this box is a small PLC that sequences the test. There's a meter up here, which is a minute meter, and it tells me how many minutes the blower motor is on during the first stage of the test. That would be up to 220 degrees. So here is the unit that holds the follower, and that's an actual Norton cam follower. So it's a Stellite pad. There's a hole in the top of the follower here where a thermocouple fits, and that goes clear down and contacts the center of the Stellite pad, so it can measure the heat being produced by the friction of the arbor against the follower. There's another thermocouple that fits in the hole here, and that is a second measurement of oil temperature, and that goes to the PC, which does the data logging. And you see there's basically some baffles built in here, and the cup is built off center so that the oil swirls round and round the cup, and this makes the oil pile up on the arbor and keeps a lot of lubrication flowing over the arbor all the time. The arbor is actually submerged about a quarter of an inch or a little better in oil. This is my strain gauge weight sensor. This is my load. It's a bucket of water. It has a valve here. It's electrically controlled. And that is opened by the PLC and allows water into this bucket. There's a set weight in the bottom of that bucket that gives me the starting weight. Go over here. Here's the oil I'm going to test. There's 125 cc's of oil in there. The box here contains the digital to analog converters that change the signals that come from the tester and feed it to the data log system here in this PC. And basically we are reading the follower pressure, which is from that strain gauge sensor that I showed you a moment ago. The follower temperature, that is the thermocouple that is buried in the bottom of the follower. The oil fan, that is the second oil temperature sensor that I showed you a moment ago. That only reads while the blower is running. So when the blower is running, it will be reading the oil temperature. When the blower is not running, that means that the temperature is at the controlled temperature. And this is the friction, and that is a reading of the amount of power that the motor is pulling to turn the arbor. And with some oils that can be a considerable amount. I have had some oils that draw so much friction that they will trip the breaker on my 1-horse motor. This is what I use for arbors. They are R12 bearings. They're similar hardness to a camshaft, so that makes a good substitute for a cam on here. So the idea here is there are basically two types of lubrication that are going to apply to a camshaft. The first is hydrodynamic lubrication. That is when the arbor is running fast enough and the follower has low enough pressure that the follower basically skis on the film of oil and the two parts never touch. And the wear is negligible at that when that's happening, or basically no wear at all. Modern engines with light valve springs and large inverted cup followers, they operate in the hydrodynamic range most of the time. A Norton, on the other hand, has a small, narrow follower and much higher spring pressure, which is necessary due to the fact that you have to control the rocker arm, the push rod, and everything else in between. Plus a large single valve instead of multiple small valves. So that means that the Norton follower operates in the area of mixed lubrication. So there's hydrodynamic, and then there's boundary lubrication. Boundary lubrication is when the protection is being supplied by a film that builds up on the arbor race or the camshaft in the motor. That film is supplied by the zinc phosphate in the oil. To build up that film on the arbor requires heat and rubbing. So to start the test, we start out with 100 pounds pressure on the follower, which is minimal, and we start out with the oil at room temperature, and in the first 7 minutes the oil is heated to 220 degrees and held there. If the friction of the arbor against the follower is enough, it will actually raise the oil temperature by itself. And if it raises it very much, then the temperature controller here will turn on the blower motor and keep it at between 220 and 230 degrees. It's been found that it takes approximately 20 to 30 minutes, depending on the type and amount of ZDDP in the oil, to form the maximum amount of protective film, which is like a glass. It's a very hard substance and it builds up on the arbor. So 20 to 30 minutes of rubbing at 220 degrees gives us a film of zinc phosphate on the arbor. After the first 25 minutes, the burner comes back on and starts raising the oil temperature, and it will raise it to 320 degrees. As the oil temperature passes 300 degrees, then the PLC over here signals the water valve to open, and water starts flowing into this bucket. As the pressure goes up, the friction obviously is going to go up, and as the friction goes up, with some oils that produces a lot of heat, other oils produce very little heat. If the oil produces enough heat to raise the oil temperature to more than 10 degrees above the set temperature of 320 degrees, then the cooling fan will come on, and the time on for the cooling fan is basically monitored by the data logging equipment over here. So we end up knowing exactly how long the cooling fan has been on, both in the low temperature and the high temperature, and that gives us an idea of the heat from friction of the oil. So the water continues to fall into this bucket and raise the pressure. At some point, the oil film and the zinc phosphate layer on the arbor is going to break down. When it breaks down, it's very sudden, and the follower touches the arbor and it lets out a screech, and sometimes will stop the motor. Sometimes it still remains turning, but it creates a large scar on the follower, and at that point the test is over. There's no point in looking at the scar. It's going to be nasty. The hotter the follower was when the failure happened, the larger, of course, is going to be the scar. But that's really not something I'm looking at because, well, like I said, once there's a scar there, the test is over. So I'm going to get this set up, and I'll show you the machine running here in a moment. So here we are. The test is running. The white paper here is basically transformer winding paper. It's oil and heat proof. The bucket is hanging from our sensor here. There's the oil temperature. It's rising as the heating element is pulsing off and on once per second. As it gets up closer to 220 degrees, then the duty cycle goes down and it levels off right at 220. Each test gets a new arbor. I've done a few of them now. Here is the data log that's being created. The wiggly green line on the bottom is the friction. The black line here is the load, and the top line there is the follower temperature. So the oil that we're testing is actually R40 Castrol. Quite low friction. And there's our follower temperature or pressure, which is 96 pounds. That's being supplied by the weight that stays in the bucket. And it's going to sit here for 25 minutes and run like this, and we will be monitoring the cooling fan cycles and allowing the oil film to build up a layer of protection on the arbor. And I'll be back again here when the test is getting close. We are now 10 minutes into the test, and oh my, that Castrol smells wonderful. Very little friction from the Castrol, so the temperature is being a little slow to get all the way up to 220 degrees. small amount of friction means the follower temperature is staying right there pretty close to oil temperature. I think maybe I reversed the colors when I was talking last times. The black line, the top one, is the follower temperature, and the red line is the load pressure. So we have reached 25 minutes. The oil temperature has not gone above 220 degrees. The cooling fan has 0 runtime. It has not had to come on yet. Basically, this Castrol is a very low friction oil. Our follower temperature is below the oil temperature. So basically, our heat from viscous friction is going to be 0. As the load is applied, the follower temperature will go up, and if the follower temperature exceeds the oil temperature, then that is heat from friction at high pressure shear, and that will be recorded as a number between 0 and 10 according to a formula that combines the heat from high pressure shear and the heat from viscous friction. So the temperature is up to 238 degrees. I should add that any of the oils that I test would still be in hydrodynamic lubrication. In other words, the lifter is not making contact metal to metal, and the ZDDP film is not being fully utilized. There may be some mixed lubrication there. And there is obviously some mixed lubrication there, because if I would have an ashless aircraft oil with no ZDDP in it, any of those I have tested would have failed about the time the oil temperature reaches 220, because they simply will not support much load. So I'm going to let this run, and I'll come back about the time of failure. Well, it hasn't failed yet, but the oil temperature is now at 303 degrees, 304, it's climbing. It'll climb to 320. And the water is now transferring into the load bucket. Our follow pressure is now up to 111 pounds. And the friction is beginning to increase a bit. I'm not sure how many pounds of pressure this oil will handle, but we're going to find out. The oil just went off. Friction's pegged. $246 pounds on the follower. Follower temperature was up to 357. And as you can see by the data log, see the friction line as the oil failed. The friction went to the moon. So that is the point where the oil film and the ZDDP layer that was on the armature broke down, and if that were a cam and lifter, it would now be toast. So this oil testing has been mainly done with high viscosity oils that I thought would likely be able to stand high temperatures of an air-cooled motor. Of course, these tests are also useful in pretty much any high-performance engine, particularly old pushrod motors. And I'm feeling pretty well that the results seem to show what I have learned over the years as far as which oils don't cause camshaft problems and which ones do. So the results of all this testing will be posted on the Access Norton site. I'll put the link down below this video. And the time that I've got into this testing is obviously quite a bit, and plus I've had to buy an awful lot of arbor races here. And many of the oils that I've tested have been supplied by people that sent it in. Of course, some of the overseas oils that are also available in the United States, I just purchased locally and tested them for the people. And so if you're running an air-cooled motorcycle engine or a Porsche or other high-performance pushrod motors in particular, you might find this information valuable. And of course there's a donate button there. Feel free to use it and help me cover some of the materials and time I've got into this. Thanks for watching.